Come down here under Use 2D Camera and begin to add our draw functions. And normally we'd be drawing sprites normally, but we need to be able to draw parts for meomotion, so we'll add that first. I'll just fast forward through the comments. So we'll start a draw transformed vertices, which is what meomotion will use. Taking the source for where the image comes from off of the texture, the scene origin, which is where the vertices are rotated around or drawn around, and the 4 points, which are pre-transformed, and the color that we want to draw them, and whether or not it's supposed to flip it. By default, the effect will be none. And first of all, let's make sure that we're not starting this without having called the begin function, which we haven't made yet, but we'll make that later after we've made a few draw calls. And this will just make a console warning for debugging purposes. It'll return if begin isn't set already. We're going to need the corners for the UV coordinates. Oops, this should be U2. We'll start with adjusting the first point so that it's relative to the scene origin, because these transformed points or vectors are transformed relative to some origin. So there's some distance from where they've been rotated around, and we need to place them where they should be on the screen. So instead of being relative to the origin of 0, they're going to be relative to where the joint would be on the screen, which is the screen origin. These are all the same sort of thing. Just got to change this to 3 and 4. Now I'll set the UV coordinates. The source rect's X coordinate, and we got to make it in terms of 0 to 1 space. So we divide it by the texture's width to get the percentage into the texture it is between 0 to 1. 1 is 100%, 0 is 0%. Hopefully you get that by now. I'll just comment it, fast forward it a bit. And we'll do the same for V. Except that it would be divided by the height, obviously, and then this would be y. Oh yeah, and this would be v. Then we'll do u2 and v2, and that'll be the bottom right-hand corner. So we have to add in the source rect width, and here the source rect height. And if we're flipping the image, then we need to flip the UV coordinates. So we'll do a logical, oops, made an error here. So that'd be a logical AND to see if it's set to flip vertically, in which case we got to exchange the two. So we'll set a temporary to be v2, set v2 to equal v1, and then v1 to equal the temp. Same idea for flipping horizontally, just a logical AND, and this time with the u coordinates. Alright, so we've adjusted our positions relative to the joint, and we've got the UV coordinates in terms of 0 to 1 space, and we flipped them if we need to. So let's add these vertices to our list of vertices, starting with position, and these all have to be vector 3s, because we'll just apply the default depth, which actually can be adjusted. So the texture coordinate is actually a vector 2, doesn't have a depth because it's just where it takes it off of a two-dimensional map. And the color, since we're done this one, we'll update or increment the vertex counter, vert count, and do the next vertex. So next position, we're using the upper right texture coordinate. And then for the third one, which is the bottom right, so lower right, it would be U2, V2. And the fourth one is the lower left, so this would have to be U1, V2. Let's do a test to make sure that we haven't exceeded the maximum number of vertices we're allowed at this point. If we have, we're going to call end verts. And end verts will be a little bit different than end, but it's basically the same thing. I'll show you that later. Underlined because we haven't made it yet. Alright, so that's it for the meomotion version of draw transformed vertices. Alright, now that we have something that can draw the different parts for the meomotion character, let's go to drawing regular sprites, like how SpriteBatch might do it. So we'll just do a simple draw first. Supplying the source rectangle, which will be optional. You could say null. If you say null, then it'll use the entire texture. For better efficiency, I'd recommend putting most of your images onto a single texture and using a variety of source recs, because you want to minimize your texture switching. A position to draw it, and a color to draw. So that's sort of your tint. If you supply white, then it'll just draw it normally. If you give it more of a red color, then any of the red aspects of the color will be preserved, and any any reduced blue or green parts of the color would be desaturated, so it would look more red, as an example. And then the flip option, which could be horizontally, vertically, default will be none. Let's just copy this line from up here. Let's make sure begin was actually called, sort of like an assertion. Width, height for x1, y1, x2, y2. We're going to make some calculations to figure out these points. And the UV coordinates again. So if our source rect has a value, or if it doesn't have a value, that's why I got the not here. If the source rect is null, then we'll set the source rect to just be the regular texture dimensions. So I'll use the entire texture. Width is source rect value, and the height is source rect value height. So we're going to need positions destination. X1 is the position x1. Y1 will be position y. X2 is equal to position x plus w. And y2 is just position y. This will be upper left and upper right. And then we'll do 3 and 4, which should be lower right and lower left. So x3 will be x plus w, and y will be plus h, because it's lower now. And x4 is to the left now, and this is the plus h, because it's on the bottom. So we'll make a rectangle, it's a temp rectangle, and it will equal our source rect's value, which we made sure that source rect had a value up here. Let's work on the UV coordinates. So x, remember that's based on the source rect, and we'll get it in terms of the 0 to 1 space, so we'll divide it by the texture width. Likewise, divide the y by the texture height. Get u2, we'll use temprect.x plus the width of it, and divide that by the texture width. And v2, similarly, v2 will be the y and the texture height, and we'll divide by the height to normalize it. So if we're flipping the texture, we'll flip the UV coordinates. Horizontally is not, we'll do a logical and it's not 0, meaning that's what we have it flagged to do. Then temporarily set temp to v2. v2 will be switched to v1. v1 will be switched to v2 via temp. Oh wait, this is actually, should be, these are v's, verticals. This should be flipped vertically, so we'll change that. And we'll check for horizontal flipping if we need to do that as well. And then if we are flipping the u coordinates, flipping the image horizontally, so let's start making our vertices to add to our vertex list. New vector 3, x1 we made, the y1, the current sprite depth, and the texture coordinate, which is just the u and v coordinate for the upper left. Set the color for this one, C1, and we'll increment our vertex count because we just finished adding this vertex. Alright, so that's one vertex. We need 4 in total, so I'll just copy these. So obviously this will be x2, y2, x3, y3, x4, y4. Colors will be the same, so you just need to change which UV coordinates we're accessing. So it'll be the u2, v1, which will be the upper right, and u2, v2 will be the lower right, and u1, v2, which will be the lower left. Should it be the case that our vertex count is getting a little high, we don't want to go over 8,192 because that's as many as we allocated. We'll call nverts, which we haven't made yet. We'll make sure our begin call is set to true for when it comes back, because it will set it to false. Okay, I'll make a copy of this and just make a few little changes to it. We'll put the copy just above it, and this one will be for 4 colors. So it's basically the same idea, except that we can take more colors. So we can tint each vertex separately, and that way you can create gradient color tinting across the image, which makes for some interesting sort of lighting and light coloring effects if you want to do that, which I will want to do, so I'm adding it. Okay, I'm just squishing everything a little bit, and we know what it all does. It doesn't need to be spaced apart too much. So the only distinguishing difference here is that we got more colors. C1, C2, C3, and C4. I'm going to go down here, squish this one a bit. So far, we have the 2 basic draw methods. They don't have any rotation or scaling or anything fancy yet, just one that has extra 4 colors for gradient shading. Let's add another basic one for drawing to a specific destination rectangle. We'll call it draw dest, so we don't have too many overloads that are the same. With the option for source rect, and then our destination rectangle, and our color, and the option to flip it horizontally or vertically or both. Let's copy our if begin wasn't called and paste it back in here. You know what, we can copy most of this and just modify it a bit. So let's do that. Just copy everything, copy and paste it, and we'll just have to make some modifications. So what's got to change here? Well, we're not getting a position, we're getting a destination rectangle. So the first thing we might want to do is change this to destrect.x and destrect.y. Same here and here. Here, 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 here. And we don't want to use W because the source rect has a different width than the destination rect. We want to draw to the destination X plus the destination rectangle's width. So let's replace this also with destrect.width and the H with destrect.height. Okay, and as far as I can tell, that should be the only thing that needs to be changed, because it's really just the destination vertex coordinates that we wanted to change. So let's just copy all this, and we'll make an overload of it for 4 colors, and we'll just paste it right above it. Okay, so I went ahead and I already modified it. So now you have C1, C2, C3, and C4, and the only other change you need to make is to change this to, instead of all being C1, it would be C1, C2, C3, and C4. Otherwise it's the same. Okay, so let's go up above our basic drawing methods after the transform vertices, and before our first basic draw method, we'll add a draw method. It's more like a SpriteBatch1 that you can scale or rotate about an origin, and it takes a single color, starting with the optional source rect. And most of the time, of course, you are going to use a source rect. And we can take a position to draw it at, optionally a specified origin rather than rotating around the center, which I have it do by default, but SpriteBatch, I believe, has it rotate from the corner by default. So you'll have to keep that difference in mind. A float for scale, a float for rotation, a color, and by default, we'll set it so that the flip flag is set to none. Let's just copy this up to here. Width, height, origin X, origin Y. Let's just copy this. This will be 3, 4, and then the UV coordinates. So if the source rect is null, if not has value, then we'll just set it to use the entire texture. If scale is not equal to 1, then we'll need to make some adjustments based on the scale. So first of all, let's adjust the scale for the width and the height. And if the origin has value, then we'll set VOX, origin X, to be equal to the origin value X scaled. Similarly for the Y times scale. We'll add an overload after too for non-uniform scaling. So let's just put this on one line, and we'll say else, and we'll set it to the default origin. The way this works is the origin default scales 0 to 1, so 0.5 would be the center, which is what I have the default set to usually. You can't really put in a specific default origin position. You can only use a percentage, which is why I'm doing it this way, because you'll never know ahead of time what the size of your rectangle is going to be. With the specified origin, you're specifying the precise number of pixels to the right and down from the corner that you want to rotate around. So when you scale it, that's why you have to scale the origin also. Let's just shrink all this a bit. Some people would freak if they see me doing this, and if the scale is 1, then there's no change to it. We can just set it normally. So we'll set the width to be equal to the source rect value width. Same sort of thing for the height. And if origin has value, then we get the origin value dot x. Same thing for the y. Else doesn't, so we'll use the default, which will typically be the center, 0.5 being 50%. Oh, scan it over, make sure there's no bugs, and once you're sure, we can save some space. That way there's just less to look at. I mean, to me this isn't any harder to decipher, but I guess some people get really freaked out from it. I'll just comment here, same, but no scaling. So x1 is the position, y1 is the position. You know all this stuff, so I'll just fast forward through it. I just went ahead and added some comments, so you can see this is upper left, upper right, lower left. Now, once we've established the scaled coordinates, because the W and H has been scaled, then we can go ahead and add our rotation in. So long as there has been a rotation, otherwise there's no point in doing the calculation. So the origin X is going to be the position X plus origin X, which is always relative to the corner of the sprite. So now we're getting the true screen origin, screen position that we're going to rotate around. we're going to use the same angle cos and angle sine. So let's just pre-calculate the result of our cosine using math. Cosine of the rotation radians. And we'll get the sine of rotation. You don't have to worry about the speed of this. Cosine sine is fairly fast nowadays. So horizontal distance 1 is equal to x1 minus origin x. And vertical distance 1 is equal to y1 minus origin y. That's the top left difference. So this distance, this horizontal distance, is going to be a negative number because it's up and to the left of the origin. So this will be the vector that needs to be rotated for the top left corner. Let's get the one for the bottom right corner. Horizontal distance 2 is equal to x2 minus origin x. So it's all relative to origin. That's why we're subtracting it that way. If you've studied vector math, this will be very familiar to you. And y3, which is the bottom right coordinate. So that'll give us the bottom right difference. Let's calculate the new x1. It'll be origin x, always relative to the pixel that you want to rotate around. So that's OX plus HD1, horizontal distance, times the cosine value for the angle we want to rotate, minus the vertical distance times the sine. So what we're doing is we're getting the rotated vertices rotated around that origin. So origin y is added to this vector, which is going to rotate around 0. So when you add the origin onto it, then it's rotating around the pixel where you want it. That's why we have the OX plus and OY plus. So OY plus horizontal distance 1 times sine plus the vertical distance 1 times cos. That'll get the y rotation for that vertex. So just to give you a general idea of what the math's doing, when I use cos, just pretend this is at 0, 0 over here in the corner. That's the origin that this math is happening around. When I use cos of an angle in radians, spanning from 0 to 6.8, which is 3.1415926536 times 2, so pi times 2, it spans from here to here and then comes back. So initially your x value is going to be 1 and it's going to accelerate towards 0 and then decelerate at -1 and then accelerate again towards 0 and then decelerate as it gets to 1 for cosine. So if you were to sort of plot that out progressively, you'd get this sort of wave, and sine's kind of, it's already ahead in a sense. So it's kind of doing the same thing, but it's offset. So if you had a perpendicular line to that and you wanted to rotate it in the same way, say you had a line here and you wanted to rotate it in the same way, then you'd use sine instead of cos because it's 90 degrees to this one. So keep that in mind. So this ranges -1 to +1, which we can use like a percentage multiplier. 0 to 100% multiplied by whatever distance gives you how much distance that line should be. So if we wanted to use a radius of say 5, then the actual line we might use would be like this. Sort of, we'll pretend that's a distance of 5, whereas this is where 1 kind of was. So we've multiplied our radius by 5, or multiplied that distance by cosine of the angle to get it to here, if the angle's 0. As the angle changes, this starts to move that way and would go to -5 and then come back. If we wanted to draw a circle, what we'd do is we'd say that as this x value changes, the y value changes as the sine wave of that angle. So it would be, the sine wave would start off at 0 when this is 1 for the same angle. And as it increases, it would go up, down, and back. If you put the two together as an x and a y, and you just keep changing that angle and plotting that x and y value, you'll actually end up going around in a circle, more like this. Something like that. So what we want to do is we have a specific vector that's, say, something like this. And it's composed of this horizontal value that we know and this vertical value that we know to get to this point. What we could do is we could rotate like a circle this and then add this vector onto the end of it as we rotate it, as though this is a 0 and we're rotating sort of something like this around like that. But then we're adding it onto the end of this, so that when we put the two vectors together, it'll give us this vector rotating around the origin, no matter what kind of vector it is. And you can expand that further into the z dimension, into depth, and then do z scaling, and you essentially have 3D graphics. But we're just working with two-dimensional transformations here. So effectively, we can rotate this line here to, say, this angle, and then rotate this around the origin and add it onto here so that it's at a perpendicular angle to this, this, and then that's our new xy coordinate, and we've effectively rotated this vector to here by combining this cosine rotated vector added with this sine rotated vector. Sine so that it starts off perpendicular. Like I said, the 0 value would be here, whereas the x value would be at 1. And then the 0 value would go up to 1 and then down to -1. Anyway, hopefully you get the idea. Then the order of operations would state that these multiplications and cosine and sine would happen first. And then when you add OX plus those, it's basically taking that result and adding it so that instead of it rotating around 0 over in this corner, it's rotating it and then adding it so that it's now translated to here, so that this is actually what it ended up doing, is rotating this vector from here to here. So that's pretty much what you did. You rotated this from here to here, assuming these are the same length. I didn't draw it very well. Of course, I suppose I could do this too. So that'd be like you did this. There, that's better. So you rotated it from here to here based on the angular change that you want.